Oh.
Sunday, Monday, happy days. Tuesday, Wednesday, happy days. Thursday, Friday, happy days. The weekend comes, my cycle hums, ready to race to you.
Oh, hey, anytime you can enter with the fawns, I think that's a good thing. But what do record players and perhaps our actual persistence within this realm that we consider our universe have in common? We conjecture ahead. Here's the thing. There we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Roolead. I don't think it rules them all, and it might be just hyper-Ruleal turtles all the way down.
Yes, it's on the back of an infinite number of hyper-Ruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. And while reading through 44, Thad's work, I came across a particular note. And if there's one thing I've learned from Professor Wolfram, it's that notes can be quite juicy. So we conjecture ahead. What was the note about? It was basically about the Clifford Taurus. And again, there are issues with this article. We need additional citation. Again, we conjecture it. But that's the Clifford Taurus. Basically, it has the property that it's essentially flat. You can basically, it's 2D. So part of the claim is like, okay, you like R2 plus R2. Basically, you can get the hyperbolic 4-dimensional space, or 3 plus 1. This is the thing. But the very interesting thing that I found here was about Nash's embedding theorem. And I totally played off Kevin Nash. Remember, there are a lot of sworn members to the NWO. I'm just saying. The Clifford Taurus is an example of a square torus because it is isometric to a square with opposite sides identified. So basically, if you take like a sheet of paper, you can actually roll it up. You can make it into like a little cylinder. And if that was really bendy and you connected it, guess what? You get a torus. You get the donut. Stand by, we're in the tastiest universe. It is further known as a Euclidean, a 2 torus, with the 2 in its topological dimension. Figures drawn and obey Euclidean geometry. Oh. Euclidean geometry is a mathematical system attributed to ancient Greek mathematician Euclid. Blah, 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 blah. Okay. He goes in. Okay, as if it were flat, whereas the surface of common donut-shaped torus, donuts, is positively curved on the outer rim and negatively curved on the inner. Although having a different geometry than the standard embedding of a torus in 3-dimensional Euclidean space, the square torus can also be embedded into 3-dimensional space by the Nash embedding theorem. One possible embedding modifies a standard torus by a fractal set of ripples running through 2 perpendicular directions along the surface. Now, I don't know how record players really work. You just have the spinning vinyl and you put like a pin on it. Apparently, there's something written into the grooves. I don't know. Might that be a wee bit fractal? I'm just saying we continue. What is Nash's embedding theorem? The Nash embedding theorems, or embedding theorems, named after John Forbes Nash Jr. I apologize, I left off the junior, Mr. Nash. State that every Riemannian manifold can be isometrically embedded into some Euclidean space. Isometric means preserving the length of every path. For instance, bending but neither stretching nor tearing a page of paper gives an isometric embedding of the page into Euclidean space because curves are drawn on the page the same arc length. However, the page is look at that, it's spinning around. I love the internet. The first theorem for continuously differentiable embeddings In mathematics, a differential function is one real variable whose derivatives exist at each point in its domain. In other words, the graph of a differential function has non-vertical tangent. Okay, cool. C1 embeddings and the second for embeddings that are analytic or smooth of class. Okay, it goes on. Basically, you have a whole bunch of magic and equations and stuff like that. Rise of the Technomancers. I think that's pretty cool. But yeah, there's additional. Where was it? Where's the ellipse? Here we go. The isometric embeddings produce the Nash-Cooper theorem, which are often considered counterintuitive and pathological. They often fail to be smoothly differentiable. For example, a well-known theorem of David Hilbert asserts that the hyperbolic plane cannot be smoothly isometrically immersed into R3. Any Einstein manifold or negative scalar curvature cannot be smoothly isometrically immersed as a hypersurface. And a theorem of Xing-Shen at Chem and Cooper said that any closed m-dimensional manifold of non-positive sectional curvature. In Riemannian geometry, the sectional curvature is one of ways to describe curvature of Riemannian manifolds. The sectional curvature depends on two-dimensional linear substrate. Okay, so all right. Cannot be smoothly isometrically immersed into R2 m-1. Furthermore, some smooth isometric embeddings exhibit rigidity phenomena, which are violated by largely unrestricted choice of F in the Nash-Cooper theorem. For example, the image of any smooth isometric hypersurface immersion of the round sphere must itself be a round sphere. So we're going to be looking for two spherical-like objects. Do they have to be the same size? Just saying. By contrast, the Nash-Cooper theorem ensures the existence of continuously differentiable isometric hypersurface immersions of the round sphere, which are arbitrarily close to, for instance, a topological embedding of the sphere as a small ellipsoid. Oh, that looks a little familiar. Basically, at least for, and again, I am not a professionally trained mathematician nor physicist. I'm a dude on the internet. But it kind of sounds like we're making big leaps. You would need to have something really fancy in order to try to pull something like this off. You would need to have it to be clearly differentiable, just and continuously able to generate stuff and things. You got a flat toric in three-dimensional space and convex integration. It is well known the curvature tensor is an isometric invariant of C2 Riemannian manifolds. Oh, we're just talking about C1. Cool. This invariant is at the origin of the rigidity observed in the Riemannian geometry. In the mid-1950s, NASA matched the world mathematical community by showing this rigidity breaks down to regular C1. He broke it down to its parts. Professor Wolfram likes to do that too. These unexpected flexibility has many paradoxical consequences. One of them is the existence of C1 isometric embeddings of flat tori into Euclidean three-dimensional space. In the 1970s and 80s, M. Grove revisited Nash results introducing convex Convex? That sounds like we might be getting a wee bit negative in the curvature there. Just saying. Integration theory offering a general framework to solve this. Oh, maybe no, I'm doing it wrong. Convex is the other way. I apologize. This, hold on. We have the internet. What's convex? I mean, I only surface curved like the exterior of it. Okay, yes, okay. My correction was correct. See? We can do this in real time. Into one algorithm that produces isometric maps of flat tori, we provide an implementation of a convex integration process leading to images of a bed of a flat tori. The revealing images reveal a C1 fractal structure. Though the tangent plane is defined everywhere, the normal vector exhibits a fractal behavior. Tangent plane is defined everywhere. It sounds like they're a wee bit tangled up, would you say? The isometric embeddings of flat tori might thus appear as a geometric occurrence of a structure that simultaneously C1 and fractal. Beyond these results, our implementation demonstrates the convex integration a theory still confined to specialists can produce computationally tractable solutions of partial differential relations. Apparently, it took a lot of computer time and stuff to generate these pretty pictures. Ooh. Whoa. Looks like it's very smooth. Oh, look at that. I mean, does that look like a garden hose? I mean, does it not look like a garden hose? Hold on. Oh no, the internet. Okay. Look, that's shiny. I mean, that's shiny. Took a lot of computing. Apparently, there's a lot of stuff really going on there. Yeah. Basically, they're trying to reproduce it. It kind of sounds like they. Okay, yeah. There's a lot of magical stuff and things going on. I haven't plugged any of that into Wolfram Alpha. I really just scrolled through to get to these pictures here, and whoa. 10 to the 19 nodes. 3D imaging and stuff and things is pretty nifty. I'm just saying. Okay, what does this all have to do with record players? I'm just saying, okay, that initial thing where it says, and of course I close it. Of course I close it when I'm actually going to go back to the original thing. Okay, we have our Clifford Taurus friend here. We'll bring you back up. Okay. Bada boom, bada bang, here we go. So, although having a different geometry, the standard embedding of a torus in three-dimensional Euclidean space, the square torus can also be embedded into three-dimensional space by the Nash embedding theory, where one possible embedding modifies the standard torus by a fractal set of ripples running in two perpendicular directions along the surface. I'm just saying I may have done a video on are we in the monopole or something where I was conjecturing. What if we just kept it as simple as possible? And okay, if you two have a tori, and basically it's like, all right, you got two circles. There's some fractal encoding of information, let's say. And one's going one way and one's going the other. I don't know. Isn't that what like the electric and magnetic fields do? Aren't they always perpendicular? Does anyone else find it odd that that's like always a thing? Magnets. How do they even work? I claim we're still learning, but that's all I got for now. Peace out, guys. Be safe, and every once in a while, it's okay to wear a cowboy hat.
We won't be going hungry if we do this. That's for sure.
Dude, my hat has made over $10 tonight.
I guess I'm gonna have to wear a cowboy hat on here with you next time too.
Howdy.
Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.